Alrighty, ladies and gentlemen, hello, how are you? This is Mr. Lowe. It's time for another exciting edition of HL Chemistry Flipped Classroom. We're going to start talking about energy and enthalpy as it relates to chemical reactions. Couple of just reminders and review things that we've talked about before. Bond breaking is endothermic and bond forming is exothermic. And in any particular chemical reaction, some bonds are broken whilst others are formed. Always love to work in a whilst, or is it whilst? I don't know. But anyway, in a chemical reaction, some bonds are broken, some bonds are formed. That's what happens when you have a chemical reaction. So we've got endothermic bond breaking happening and exothermic bond forming happening. And so whether a reaction is going to be endothermic or exothermic depends on the strength of the bonds you are breaking. So the bonds in the reactants would be the ones that you're breaking, at least some of them, and you're forming bonds when you're making the products. So in an exothermic reaction, the reactants bonds have more potential energy and the product bonds are more stable. So we're going from a higher potential energy state to a lower potential energy state, from a less stable state to a more stable state in an exothermic reaction. In an endothermic reaction, it's exactly the opposite. The products bonds are the ones that have more potential energy and the reactant bonds are more stable. And when I say potential energy, we mean these bonds have the potential energy to break and to form some other stronger bond that's going to release a bunch of energy. So basically, in an exothermic reaction, we're breaking weaker bonds, but forming stronger ones, and the net overall is that energy is released. So a little analogy, and you don't necessarily have to write this down unless you want to, but this guy up here at the top of this crazy old rickety ladder, he has a lot of gravitational potential energy, but he's also unstable. So he could move down the ladder, he would become more stable, as he went down, but he would also have lesser potential energy. This is exactly the way an exothermic reaction works. The reactants are at a high potential energy state but unstable. They drop down to a lower potential energy, more stable state, releasing energy in the process. So, while we're on the subject of crazy, unsafe ladders, there's some other fun ones that look like. I don't know if I'd want to be that guy up there looking down on that chimney. That seems dangerous. I don't know about that. And this is my favorite, when in doubt, just stand on a few buckets. But in any case, all these gentlemen could increase their stability by just going down the ladder a little bit. They would be more stable. Okay, so some things about kind of just some random facts here, I guess. When we talk about reaction enthalpy, the unit is kilojoules per mole. And basically that means the reaction would occur when the reaction occurs a mole number of times, I guess. That's the amount of energy that we're getting. We're going to talk about reversible reactions in another unit, but if you took a reaction and you just flipped it and you wrote it exactly backwards, in other words, you switched the reactants and products, that would switch the sign of the delta H for that reaction. And so that's something that's going to come up down the line. And just another couple of random facts that you should know. It's clear from the IB syllabus that you should know that combustion is exothermic. And, yeah, fire is hot, okay? Combustion is exothermic. That's something that you should know. You should also know that neutralization is also exothermic. Neutralization is when an acid and a base combine. So those two types of reactions, for whatever reason, IB has deemed it that you know that they're exothermic. The combustion thing should be common sense, I would think, but you never know. Some more terminology here. So reactions need energy to get going. The piece of paper that I hope you are taking notes on, that can burn. So the paper's in the room, the oxygen's in the room. The paper doesn't just start burning, though, because you need some activation energy to get started. You need to touch it with another piece of flame, perhaps. And that would supply the activation energy to actually get the reaction going. So this definition is the minimum molecule kinetic energy needed to begin a reaction. This actually gets into a little bit some stuff from topic 6, but as always, let's be very careful with our definitions. This is the energy to get a reaction going. If you were defining this on an IB exam or one of our exams, if you leave off minimum, you wouldn't actually get full credit. They're very picky about some of these definitions. And then another thing is a catalyst. A catalyst speeds up a reaction by providing an alternate pathway with a lesser activation energy. So catalysts, they're not reactants, they're not products, they're something else that we add. And there have to be some type of chemical, not heat or anything like that, that we add to reaction to speed them up. They are not used up in the reaction. They might be changed by the reaction, but whatever change they go through will be reversed by the time the reaction's over. So they're a thing, an actual chemical you add that speeds up a reaction. For instance, a reaction we may have seen is decomposing hydrogen peroxide by adding manganese 4 oxide, a black powder makes that reaction speed up. So there's lots of biological catalysts as well, enzymes they're called. And both those things, like I said, it's stuff we're going to talk about more in the next unit and just kind of touch on a little bit here. But something that you should know the general shape of are called enthalpy level diagrams. So they show the changes in energy, potential energy, as a reaction proceeds. You should at least sketch these two graphs and put the labels in here. So like I said, in a exothermic reaction, the reactants have higher potential energy than the products. So energy is released overall. We do need to put some activation energy in to get the reaction going, but overall an exothermic reaction is a downhill process overall. So it has this shape. In an endothermic reaction, we start at a lesser potential energy and go to a higher potential energy. It works very much like going up a hill. You know, you'd have to put energy in overall to get from here to here if you're going up a hill. So the actual delta H is this distance in the red here, the difference between the reactants and the products in both cases. The activation energy is the energy to get from here to our starting point, or our top of the hill, if you will. So in an exothermic reaction, we put in a little bit of activation energy, and then we release energy the rest of the way. So just know the general shapes of these, know what endothermic exothermic looks like. We'll talk about them more in class and practice, and there's a bunch of other things we could talk about with these, but we'll call it good for now. What I would also recommend that you sketch is a catalyzed versus uncatalyzed reaction. So you can just sketch this really quickly, and the most important thing to note is that the delta H does not change. The starting point and the ending point is exactly the same. Catalysts just lower the activation energy a little bit, but they keep the delta H the same. Okay, so at this point I'm going to define a few different things, and this can definitely get confusing for people, but we need to define these things very precisely. We'll certainly practice with it a lot in class, but the first thing I want to talk to you about is the standard enthalpy change of reaction. So that has this symbol, delta H with a little theta. Its unit, I already mentioned, it's kilojoules per mole is the unit we usually use for these. So every reaction is going to have a certain standard enthalpy change of reaction. And the definition of this, because there's a bunch of things that could affect the enthalpy change, the definition of this is the reaction must be occurring when conditions are standard. In this case, but what we mean by that is 101.3 kilopascals, 298 Kelvin, 1 molar solutions if they are solutions. Materials must be in their standard state. So for instance, if water is one of the reactants, it would need to be a liquid because that's water's temperature, that's water's state at room temperature. If oxygen was one of the reactants, it would have to be oxygen in the gas state. So that kind of thing. And the exact molar quantities in the reaction must completely react, because the amount of stuff that you react makes a difference in terms of how much energy that you get. And you know, this should be obvious, but it seems like some people sometimes have a hard time understanding it. So another, I guess, for instance here, this is another example. You don't necessarily have to write down all this stuff unless you want to, if you think it would clarify. This is a famous reaction. It's called the thermite reaction. You take iron 3 oxide, which is rust, and you react it with aluminum. It makes aluminum oxide and iron. It has a very large negative delta H. It's very exothermic, puts off a bunch of energy. So when you see this reaction, you know, if you're thinking about it, the question you should ask yourself is, well, under what circumstances do we get this much energy? Because think about this. Let me show you this reaction actually presented a couple different ways. Here, what you're looking at is a guy, he's got just a iron sphere here that's covered with rust and some aluminum foil, and he's going to smash them together. Whoops, hold on. Okay, back at it here. He's smashing these rusty iron ball with the aluminum foil. It makes a nice little pop there when he does it. So he's just reacting basically just a little tiny bit of aluminum on one ball with a little rust on the other, and we get that nice little spark there. On the other hand, we could do this reaction on a bigger scale. This is a flower pot. It's got quite a bit of aluminum and iron trioxide in it. So we get a bunch more energy there.
You can see all that really quite nice molten iron.
So we did it the second time. You got a bunch more energy there because you reacted more stuff. I mean, that should make sense. So the question is, how much stuff do you have to react to get this exact amount of energy here? And the answer is, first of all, you have to be under standard conditions, and you have to react exactly 1 mole of this with exactly 2 moles of this. Any amount different than that, you're going to get a different amount of energy. So another somewhat related thing, but different, is called enthalpy of combustion. And you can look up in the data table enthalpies of combustion, like burning stuff, right? So hydrogen, sulfur, ethane, propane, propane like a grill. So for instance, we look at propane here, we see this amount of energy. So basically what it's telling us is burning propane gives us this amount of energy, but how much propane do you have to burn to get that much energy? If you burn a little bit of propane, you get a little bit. If you burn a lot, you get a lot. How much to get that much energy? Well, it depends on what the definition of enthalpy of combustion is. It turns out the definition of standard enthalpy of combustion, which is what that table shows, is the energy released when 1 mole of a substance undergoes complete combustion at 25 Celsius and 1 atmosphere pressure. When we were talking about that other table, all of those things are only true when you combust exactly 1 mole of something, and you have to completely combust it. So what might happen is, for instance, there's ethane. Ethane is on the previous table here, and we have an enthalpy of combustion of 1561. So what reaction is that that's going to yield negative 1561 kilojoules of energy? What chemical reaction would yield that? And we have to write it. So let me get out my whiteboard here. So this is going to be a combustion reaction. We need to write it with state symbols, and that's a gas that's given to me right there. Now I know combustion is always a reaction with oxygen, which of course I know that's a gas at room temperature, to produce CO2, which I also know is a gas at room temperature, and H2O, which is a liquid at room temperature. So everything has to be in its standard states. So I'm going to balance it. So let's see, 2 carbons, I put a 2 there to balance it. 6 hydrogens, I put a 3 there to balance it, and then I go 2 times 2, that's 4 oxygens, plus another 3, that's 7, and I think, oh man, I can't put any whole number here to get 7 oxygens, and when we did this before, what we do is we double everything. We would put a 2 here, we would put so we would put a 2 there like that, and then we'd put a 4 here, and then we'd put a 6 here, which makes 14 oxygens, that's 8 plus another, and we put a 7 there. Now the problem with that is now there's a 2 in front of this. Now I'm combusting 2 moles of ethane. So that cannot be the standard enthalpy of combustion. Standard enthalpy of combustion requires 1 mole. Now I got 2. So when I balance this, I have to balance it in such a way as to not put a coefficient in front of that, in front of the ethane there. That coefficient has to remain as 1. So I'm going to balance the hydrogens, put a 3. I'm going to balance the carbons, put a 2. There's 7 oxygens. There is one way you can get 7 oxygens here, which is to not use a whole number, to use a fraction, 7 halves or 3.5. 7 halves times 2 is 7. So that's the way I have to write this equation, so that I get the standard enthalpy of combustion, because the standard enthalpy of combustion requires producing 1 mole. So you are not allowed, when writing standard enthalpy of combustion equations, to put any kind of coefficient in front of that. So there's the answer to that one. That's just the same thing I had there on the whiteboard. So if we look at another one, C2H6O. So again, I'm just going to write the combustion reaction, and I think I'll just go ahead and cut the result here. That is a liquid. There's a way to look that up. Otherwise, we should know that this is an oxygen. This is a gas. This is a gas. This is a liquid. In this case, we end up balancing it, and we don't have to put a coefficient in front of there. 3 times 2 is 6 hydrogens. 2 times 2 is 4 oxygens here, plus another 3 is 7. So if I put a 3 there, that makes 6, plus this one, that makes 7. So it's balanced, and there's no problem with having to put a 2 here in front of this or anything. So that one's good to go. Here's one more. I want you to try this one and give it your best shot. You can do it. This is going to be one of your reactants. Oxygen is going to be the other, and then CO2 and H2O. And then you just have to balance it without putting any kind of coefficient in front of this. And what it might require you to do is put a fraction, a mixed number, if you will, here in front of the oxygen. So go ahead and give that a shot. So that's what that one looks like. Balance the carbons first by putting a 6 there. 14, we put a 7. That's 19 oxygen. 6 times 2 is 12 plus 7. That's 19. So normally, you know, we would double everything and do all that, but it's actually kind of easier. You don't have to do that. Just put 19 halves in front of here, and then that's good. That is the reaction that would be the standard enthalpy of combustion of hexane, that's called. And I know this can be a little confusing. It's definitely something that we'll talk about and practice some more with, but just want to kind of give you an introduction with that for now, as well as another piece of terminology here, which is the enthalpy of formation. In your data booklet, you'll see another table that has this data, and it's called the enthalpy of formation, and we're going to talk about what that means and where that comes from. But we've got various substances here. Enthalpy formation is a completely different thing. Enthalpy change of formation is the energy to form 1 mole of a substance of a compound from its elements in their standard state at 25 degrees Celsius and 1 atmosphere pressure. So in this case, instead of burning something, we are constructing it from elements only. So for instance, we might look up on a table and we might see the standard enthalpy of formation of calcium carbonate. And our job might be to write the reaction that would represent that standard enthalpy of combustion. So we have to write a reaction that matches this definition. So with my handy whiteboard here, so the definition is forming 1 mole of a substance from its elements. And I know that's a solid because it's an ionic substance. So that's the product. That's what I'm forming. The reactants are going to be the element calcium because it's got calcium in it. The element carbon because it's got carbon in it. That's a G. And the element oxygen. Oxygen is a diatomic element, so I'm going to put O2. It's also a gas. So the 3 elements that make this up are my reactants, and then I just got to balance it like usual. I cannot put any kind of coefficient in front of here, but I can balance the oxygens by just putting 3 halves there. So now I've wrote an equation that matches that definition. I have only elements over here forming my product. And so that would be the standard enthalpy of formation of calcium carbonate. And that's just the answer. Same thing I had written on the board there. Okay, here's another one. I'd like you to try it. I know this can be a little confusing, but give it a shot. You can do it. This here, put that as a product. Put that on the right side. And on the left side, figure out what elements build this and put only elements here on the left. In this type of situation, you're only allowed to write elements. So give it your best shot. Again, I know it's confusing. See if you can do it, and we'll come back in a second. Okay, so that's what it looks like. We have to remember that both hydrogen and oxygen are diatomic elements, so we have to write them as H2 and O2. Then we have to balance it, put a fraction in front of the oxygen to get only 1 oxygen, and that's what that should look like. As far as knowing this is a liquid, again, there's a place where you can look this up. But anyway, I know that's tough to wrap your brain around, but we will talk about it more. We'll practice more. Thank you very much for watching, and we will see you next time.